Hello chemists, this is Ms. Placino and you're watching lesson 7.5 on gas laws. Today we're going to look at how gases are going to behave under changing temperature, pressure, and volume. This lesson is going to use a gas law simulator. So what I'd like you to do, maybe in a separate tab or something, Google UTexas gas law simulator. And click on that first link, and that should give you a pretty easy to use gas law simulator. And we'll talk more about what to do with that in just a moment. So goals for today's lesson: you want to be able to understand the relationship between pressure, volume, and temperature of a gas. What happens as we change these and how it impacts a gas. We're going to be performing calculations with all sorts of gas laws, eventually leading up to that combined gas law. And finally, be able to make some predictions and explain observations using the gas law. So before you dive into this lesson, if you take a look at the workbook or the notes, you'll see that you've got three different gas laws: Boyles, Charles, and Gail Sacks, where you're manipulating two of these three variables and keeping the third constant. What I'd like you to do is pause this video and play around with the simulator a little bit. Try to make some predictions about the relationship between pressure and volume, for example, with Boyles Law, and then actually go through and run the virtual experiment. Keep temperature constant, play around with the volume, see the impact it's going to have on pressure of a gas. Repeat that for Charles and Gail Sacks, and then come back and review when you're finished. Right, so really important to try that out. Don't just dive into the notes without, taking a couple minutes, even if it's just 5 minutes or so, to play around with that simulator. Okay, I'm going to assume that you've used the gas law simulator and you're just kind of checking in to review. We'll start with Boyles Law, and I'll never really ask you to recite what Boyles Law is. You should just know the relationship between the pressure and the volume of a gas. It's an inverse relationship. As pressure increases, volume decreases, and again, this is at a constant temperature. So you can imagine that I've got something like a balloon. So I've got a flexible volume, and as I change the pressure on the balloon, it's going to distort its shape and its size. We're going to see this type of relationship, again, that inverse relationship. As pressure is high, volume tends to be low. Volume gets bigger as pressure decreases. And again, temperature is maintained constant. We can express that mathematically with this equation. P1V1 equals P2V2. Again, that kind of expresses, though, if pressure is going to, increase as we go from initial to final, volume would have to decrease to keep that relationship constant. So another way of thinking of P1V1 and P2V2, the ones are like the initial set of conditions. The twos are the final set. So we're going to take our closed system, change it somehow, pressure or volume, and then predict what the new pressure or volume would be. It doesn't really matter what unit you use for volume and pressure, just be consistent. In other words, if you've decided that you're going to have P1 in terms of torr for pressure, P2 needs to be in torr as well. No mixing and matching. You'll end up with very strange answers. Next law you played around with is Charles' Law. Charles' Law looks at the relationship between temperature and volume at a constant pressure. So as temperature increases, we see volume increasing. Again, you've got maybe something in a balloon, or they use that piston or the syringe with the plunger that can be pushed down or pulled up. And as temperature increases, if the pressure is maintained constant, the volume has to increase. Think about what's going on. You've got your particles moving at faster and faster speeds. That's the higher temperature. They're going to hit the wall and cause the volume to expand. You'd get a graph that looks something like this. Temperature, volume, direct relationship. We can express that mathematically. V1 over T1 is equal to V2 over T2. Again, kind of thinking of the ones as initial and the two as final. You don't have quite the flexibility when it comes to units and Charles' Law. Temperature has to be in Kelvin. Celsius won't work. Fahrenheit won't work. It has to be in Kelvin. Volume, sure, use any volume unit you want. Liters, milliliters, gallons, cups, I don't care. Just be consistent. Let's think about this. We've got temperature in the denominator. If you're working in Celsius or Fahrenheit, what's a possible value for temperature that's really going to mess up your fractions? Yeah, it can be 0. Temperature can be 0 in Celsius or Fahrenheit, which would lead my volume to become undefined. That doesn't make any sense. Also, in Celsius and Fahrenheit, we can have negative temperatures, which would lead to a negative volume. That also doesn't make any sense. We need to work in Kelvin. It's an absolute temperature scale, cannot be 0, and we will not see negative numbers. And the last of the 3 that you played around with is Gail Sacks Law. So that's the relationship between pressure and temperature at a constant volume. As the pressure increases, the temperature will also increase. Again, we're keeping volume constant. So you have to lock the syringe, or the plunger, I should say, on the syringe in the simulation. And as you increase the temperature, you get those particles moving faster. And since the volume is fixed, it can't move, it can't expand or contract, the particles are going to be hitting the wall with greater force, so we see a higher pressure. So we'll see this gas law chart again. Direct relationship between temperature and pressure. As temperature goes up, so does pressure. Pretty similar looking formula to what we just saw before. P1 over T1 equals P2 over T2. You know what I'm going to say next about units. You have to work in Kelvin for temperature for the exact same reason. We don't want any negative pressures or any undefined pressures. Just be consistent with the pressure unit. Okay. Before we get into any new formulas, I want to talk a little bit about mixtures of gases. So in the simulator, you were able to use 2 different sized gases. Little tiny atoms, we're going to assume that's helium, and then larger, also like monatomic gas, we'll assume that's argon. So you have a mixture of gases. You probably saw gas A, which we'll call helium, moving at a faster speed, even though the gases were at the same temperature. If you didn't try it out, you don't believe me, pause this video, go into the simulator, put A and B in there, and you'll definitely see a difference in speed. Temperature is the measure of average kinetic energy. Of a sample. So kinetic energy is the energy of motion. So how is it possible that 2 gases, 2 different atoms at the same temperature, have the same average kinetic energy but different speeds? The formula for kinetic energy is 1/2 mv squared. Ke, hopefully it's obvious, stands for kinetic energy. M stands for mass. And V stands for velocity. Kind of just think about that as speed. You'll spend more time in physics with that term. So if I've got 2 different massed objects, in this case gas particles, at the same kinetic energy, they're going to have to be moving at different velocities. That's the only way to keep Ke constant. So you've got 2 different masses of atoms, helium versus argon. Helium, really light. Argon, about 10 times heavier. They're going to be moving at very different speeds, even though the average kinetic energy, the temperature is the same. So just be aware of that. Okay. So we talked about the 3 different gas laws, Charles, Boyles, and Gail Sacks, and you might be thinking, oh man, how am I going to remember all of that? Well, don't worry, New York State feels your pain. They've given you this, the combined gas law. You might be thinking, well, wait a second, no, we never had all 3 of the variables at the same time, we're only looking at 2 of them. Well, don't worry, don't panic. Think about Boyles. That's the relationship between pressure and volume at a constant temperature. You were just to cross out temperature, it sets up the relationship for you. P1 V1 is equal to P2 V2. Check your notes. That's the formula. So it is provided. You just have to know which ones of these to kind of, cross out or ignore. all of those gas laws really can be connected through this combined gas law. And this one, like I said, is provided on the reference table. Let's try out a practice problem using the combined gas law, because that's definitely more complicated than Charles, Boyles, or Gail Sacks. So let's take a look at practice problems. All right, I'm going to take a look at actually I lied. Let's do question number 5. An unknown gas takes up a volume of 192 milliliters at 500 torr and 50 degrees Celsius. When the pressure is decreased to 100 torr and the temperature is raised to 94 degrees Celsius, what will the volume of the gas be? Whoa, lots of numbers. Let's see. I've got an initial volume, an initial pressure, and an initial temperature. I'm also provided with a final pressure and a final temperature, and I'm asked about volume. So since I have all three, temperature, pressure, and volume in my problem, this is a surefire sign that I've got to use the combined gas law. P1 V1 over T1 equals P2 V2 over T2. All right, pressure, 500 torr initially, 100 torr in the final. We're in the same unit. These can be plugged in directly. Oops, that should be 500 initially. My mistake. Sorry. 100 torr. I've got volume, 192 milliliters. And I'm looking for the volume, so I'm just going to leave that as V2. I've got my temperatures. Great, they're in the same unit, so I can just plug in directly. Wait a second. No way. I got to get that out of Celsius and into Kelvin. It's as simple as just adding 273. So 50 plus 273 gives me, what's that, 323 Kelvin. Same type of calculation, 94 plus 273 gives me 367. Okay. If you're wondering, where did that 0.0 go? Did we lose the sig fig? No, we're okay. We have no places after the decimal point or adding, so I've got a total of 3 sig figs in each of those temperature measurements. Go ahead, pause the video, grind through the math, and solve for V2. All right, so I take 592 times 367. Then I can divide it by 100, divide by 323, and that should give me my answer for V2. So let's just kind of see what the calculator gives you. We'll deal with sig figs. I got 1090.77. Let's deal with sig figs. I'll assume that all of the values provided have been measured, 4 sig figs and 400 and 500 and 100, only 3 sig figs in my volume and my temperature. I'm left with 3 sig figs. We'll let you get away with that, now putting it into scientific notation. What's my unit going to be? That's a volume. I had V1 in milliliters, so it makes sense that V2 will also be in milliliters. That's it. All right, obviously you've got questions on that page to practice with. I would really recommend doing so. Make sure that you know when to use the full, complete combined gas law and when just to use one of the kind of derivatives of this to solve problems. All right, thank you for tuning in, and I hope you found this lesson helpful.